Good afternoon. That's better, I think. We have had a very busy morning. I don't know if they've told you, but we've been considering therapy at the other meeting, and it's been a very enjoyable and rewarding and tiring morning. But very interesting and very promising from the standpoint of AT, which is what we're here for. What I'm going to talk to you about is, let's see if we can get this going in the right direction. I think I pressed the wrong thing. Yeah, I can press these too, can I? Okay. Going to talk to you about the development of a group of drugs that we started working on about 2002. First to prove that there was a chance that they might do something, and then that took 3 years. And then to develop a better set of drugs that would cross the blood-brain barrier and move to the cerebellum, which we think is the central target for any treatment for AT that would address the ataxia. So there may be more. It may not be that simple, but I'm almost certain at this point that the cerebellum will be at least one of the primary targets for treatment. SMRT are we've called them the smart drugs, not because they're smart, but because they're small molecule read-through compounds. And we take parts of that. Small molecule is because if it's a molecule over a certain size, it won't pass through the barrier that protects your brain from other compounds. This is a significant problem in making drugs that affect the brain. And all of the drug companies know this. And we knew this, and we were going to set up a screen where we would look at maybe 35,000 compounds over a period of 6 weeks with robots. And we needed to pick the library of compounds that we would use. So we selected libraries of small molecules exactly for this reason. Read-through is meant to correct a nonsense mutation. And this is what we mean by a nonsense mutation. This would be the normal DNA coming across here. The DNA is then translated into RNA, but you don't have to worry about that at this point. The only thing you need to look at is that there's supposed to be a C here, and in this example, the C has a mutation into a T, and that alone can put you in a wheelchair because it creates, instead of a glycine, a glutamine, I'm sorry, it creates a stop. Now, a stop is a necessary code. Even when you're reading a book, you have a period at the end of a sentence, right? The reason for the period is to tell you, now we're going to go to another thought. This is the end, this is the beginning. This is what these stop codons do. The only problem is this stop codon is not supposed to be here. There's supposed to be a code for this amino acid, and there should be really only one place to stop. That's at the end of a molecule. When you're making a new protein, the machinery has to stop at the end. So if you stop here, you get a very small ATM protein, and that falls apart. It's not stable. It's not effective for one reason or another. You're left with a protein, or maybe no protein at all, that does not function. And that's one of the steps in developing AT. Okay? So these drugs now will basically influence the reading of this RNA to make the protein. And if there's a stop right here, these drugs, which were discovered in the 60s actually, they were mainly at the time discovered among antibiotics that were being tested on bacteria. It was very clear that something like streptomycin, one of the early antibiotics, it's not used anymore because it makes you deaf. This antibiotic would influence the interpretation, the reading of RNA into protein. And that's exactly what these drugs do today. They influence the read-through of this stop codon here, which is created by the mutation, and they try to correct it, and it actually opens a door and allows this to continue so that you end up with a protein even if you have a stop codon there. These were the screens we did. They are not meant for you to follow each step, but it's to show you that we start with a library. This is work done in the test tube. This is work done in cells from AT patients so that we can follow up on this to check whether these concepts are still true. And a drug here, if we start with 35, we end up with 23 that seem to have the activity we want. And from that, we picked the best one that we thought we would work with. And it had activity, and then we looked to the chemists. We have a very good medicinal chemist at UCLA, Michael Jung, and we looked to him to make derivative compounds where he would change parts of the molecule to see if he could make it better for the purposes of developing a drug that would still have the activity, but then we needed to find out which drug would be best. And when you do this, you end up with a group of drugs. In this case, we called it the BZ group. And those would define now a chemical structure that we could then associate with with that molecule or the group of molecules. And that's what the drug companies are interested in buying. They will take a compound or a group of compounds like that and try to work to select one to bring this to market. It's a big job to bring a drug to market, and I'll tell you more about that in a moment. We went back 3 years later when we thought we were a little bit smarter, and we were. We were more efficient. This took us a lot less time than this did, and we ended up with another 22 hits, and from that, 4 compounds that we liked. And at this point, we have made, I don't know how many derivative compounds, and we have 3 groups of compounds. They're called SARs. That means a group of compounds, and those are the ones that we have been working with to make sure that they are patented, because a drug company will not take over any project from you if you don't own the intellectual property. They're not going to put any money of their own investment into that drug or that group of drugs unless they know that they can buy the royalties and be protected from any other competition. So you must patent this as you go. So in the past year and a half, this one is already, it's published as a patent. It's online. You can get the structures and look at them. And this one we have just filed with a second group of patents. We are also developing, along with the help of Dr. Levin here and several other people at UCLA that are experts in making stem cells. And we have made stem cells from individual AT patients that we take a skin fibroblast, and he'll tell you more. Have you already spoken, Marty? No? No? Later. He'll tell you more about this, but basically we take a skin biopsy and grow the fibroblasts, and then we can induce, with these genes and chemicals, we can induce that cell to become pluripotent, where it has the ability to develop into most other kinds of cells. And one of those that we're interested in is the neural pathway, because that's the pathway that seems to be affected in AT. Once we have these cells, which we do now, we test them with these drugs to see if the drugs will do the same thing, specifically on specific types of nervous tissue cell. And that, again, is something that we need to know in order to develop a drug that we can bring to market. And you can see here by these are the types of stains. They're markers that tell us, yes, these are neurons. Unfortunately, there's too much light to see the pictures. These are all microscopic slides. And this is a marker for astroglial cells. And we have seen Purkinje cells. We can begin to work with them now. This is all very recent data. And Dr. Levin has another group of cells that he's made from some Australian patients, and we will work together to test these drugs to see which one is best.